Hey folks, Professor Fiore here. Today we are going to look at a design for a direct box. What's a direct box? Well, the first thing I'm going to say is, if you haven't checked out the videos on the op-amp based phase splitter, you're going to want to look at that one first, because this is based on it. Essentially, a direct box is sort of a practical realization, portable practical realization of a phase splitter for a musical application. What sorts of requirements do we have? Basically, what it's going to do is take an unbalanced input from an instrument. Classic example would be bass guitar. And, that would be a high Z source, a high impedance source. And then we're going to turn that into a balanced low impedance signal that we can drive a recording console with, or a PA console. Now, some instruments, like if you take a modern keyboard, a professional quality keyboard, would already have a low impedance balanced output on it, either an XLR connector or a TRS 1/4 inch style tip ring sleeve. But if you have some vintage keyboards or other kinds of instruments that you might be interested in, it may just have your standard 1/4 inch high Z output. Okay, so we need to take that and put that into, like I said, a low impedance balanced signal. If we're going to run this a fairly far distance, a long cable off to, like I said, maybe a PA mixer or a recording or something like that. So very handy little device for using that. Low impedance balanced system will have much, much lower noise than your typical unbalanced high impedance system. All right. Okay, so what do we need? Well, obviously we want something that's low distortion and has a very wide, flat frequency response covering the entire audible range. We don't want this to impart any of its own color onto the sound itself, right? We don't want to change the timbre of the sound. We just want a perfectly faithful reproduction. It's just that we want two outputs, one that's in the original phase and one that's in the anti-phase, 180 degrees out of phase. That's all we really want. We might require an input pad for the circuit. For example, I mentioned using a bass guitar. Well, what if you want to also get the sound of the bass guitar amplifier? Now, you could just put a mic in front of the loudspeaker, right, for the bass amp. That has pluses and minuses, because you'll also pick up any sound of quality changes from the loudspeaker itself. But, maybe there's just something about the overdriving of the amplifier that you like. Well, you could tap off of that and use that as your signal. Unfortunately, that signal is going to be a lot bigger than what you're going to get out of the guitar itself, right? Where you would be looking at maybe a few hundred millivolts coming off the amplifier, you can be looking at tens of volts, right? Maybe 100 volts in an extreme case, all depending on how big the amplifier is. So we're probably going to need to attenuate that 20 dB, maybe 40 dB, all depends on how big it is. We would like a relatively straightforward DC powering scheme. Now, one possibility is to use 48 volt DC from a phantom powering system, but I'm going to say right up front, that's great. If you have some professional PA equipment or recording gear, but if you're like many people and you're on a budget, you might not have a system that has switchable phantom power for each of its inputs. And maybe you're in a very sort of tight kind of situation. You're in a little club somewhere, and same sort of situation, right? You don't have that. You've got this little tiny mixer. It doesn't even have any phantom power capability. So I want to look at something that's going to be a little bit more flexible than that. Now, the ideal thing would be to perhaps have phantom power as an option, but I'm going to forego that. I'm going to tell you right now, we're going to forego that just to keep sort of on track here. I don't want to veer off too far. The last thing I want to point out are what I call anti-oops features. Your mucking around on a stage that's dark, in between sets or before everything starts up. You can't necessarily see everything all that well. You don't want to just, accidentally do something a little goofy and have that blow up your circuit, right? Okay, so let's take a look at sort of a possibility, all right? So what I have here are two op amps, and this is essentially the phase splitter configuration, the op amp phase splitter configuration that we looked at in a preceding video. There are some things added to it, though. All right, so the first thing I'm going to point out is the op amp that I've chosen, right? So this is the input buffer amplifier. This has a gain of 1, and down here, if you haven't noticed, this is the inverting part of it. This is essentially, voltage gain of -1. This is a gain of +1. I've thrown in here a very high quality op amp, an NE5534. You can also get a very similar one, an NE5532. Low noise, good bandwidth, good slew rate. Really nice op amp. This device came out in, I think in the early 1980s, maybe something, middle 1980s. I'm not exactly sure. So it's been around for a while. It's still considered a very good op amp for audio uses. And the nice thing is it's relatively inexpensive and it's widely available. Not saying it's the best op amp you can use, but it's a nice op amp. All right. There are certainly op amps available that have, for example, lower noise, okay, or that have higher slew rates and wider bandwidths. But this is a nice, like I said, relatively inexpensive op amp. Another choice would be to use the what I would call the first generation BiFET op amps, like a TL072, 082. The old National Semiconductor part would have been an LF353. You could use like the 411, 412 series, the LF411 series. That's an improved version. Those are also really nice. There are some subtle differences in using them, and that's one of the things I want to go through. All right, so the first thing I want to point out is power. I have chosen to use a pair of 9-volt batteries. Why? They're widely available. So if you don't have phantom power, I can guarantee you can get yourself a couple of 9-volt batteries. And by using split, in other words, a plus and minus 9-volt, I don't have to worry about coupling capacitors. I mean, I could bias this with a single polarity power supply, all right, using just one 9-volt battery, but those are parts I don't want to deal with. I don't want to have coupling caps, especially if I'm using this for a low frequency application like a bass guitar, all right? I don't want the phase shifts. I don't want the tonal coloration, anything like that. So I'm going to go with plus and minus 9-volt batteries. Now, you might be thinking immediately, what's the deal with these two diodes off the power supplies, D3 and D4? I mean, they're just going to be forward biased, right? So what the heck are they doing? By the way, there would be a switch. You would have a DP-DT switch right in here because you don't want you don't want power turning on, right, all the time, when it's sitting in the van somewhere, right? So you want a power switch. Another possibility is to have switched input. You can buy 1/4-inch jacks that have switches built in them when you plug into them, and you could use that switch to generate the closure for the battery. But in any case, right, however you want to do that, those are some practical details. The purpose for these, this is what I would call an anti-oops feature. What happens if you take a battery and you put it on backwards, right? With a 9-volt, of course, the two terminals are on the same side. They're different shape, but they're on the same side. And, in a darkened club somewhere, it's very easy to accidentally put that battery on backwards. Well, with most op amps, if you put the power supplies on backwards, you blow up the op amp, right? It doesn't, explode. You won't know it, but you'll fry the op amp because there's no current limit. So that's what those diodes are there for. If you put the batteries on backwards, you reverse bias the diodes. There's no current. Op amp is saved. Yay! A nice anti-oops feature. Right? Another good anti-oops feature would be protection for output short circuit limiting. You don't want to accidentally do that and blow up the op amp. Most op amps that you would use, the vast majority of op amps that you would use for an audio application these days already have built-in output short circuit limiting. So you really wouldn't have to use something extra for that. You know, if you're going to do something with like really, really high frequencies, that might still be an issue for certain op amps, or if it's a very old design op amp, that would be an issue. But like I said, for pretty much any modern audio op amp, it's going to have output short circuit protection. All right, so what's with the other two diodes on the front end? Well, that's another sort of anti-oops kind of thing. They're there to make sure that the differential input voltage never exceeds around 3/4 of a volt, because one of these two diodes is going to turn on. In other words, if you put too large of a signal out here, you could very easily blow up the op amp. You have to keep that differential input voltage to a reasonable range. So that's what they are there for. They're there to clip a signal that's too big. All right? Don't blow up the op amp. Our in over here serves as a current limiter in association with these. Now, some op amps have these built in. As a matter of fact, the 5534 has them built in. And if you chose this op amp, you really wouldn't need these diodes. But there are plenty of other op amps, audio op amps, that don't have them. So you would like to put them in for something like that. All right. Okay, so what's with the extra resistor cap things going on here? All right. So if this is just a non-inverting buffer with a gain of 1, what's with RF1 and CF1? Why are they there? Okay. Well, they're there to minimize DC offset. I don't want any DC offset on this thing. So we have to balance the resistance seen from the inverting and non-inverting inputs. Well, I've got this current limiter out here for Rn, all right, that's coming the plus. I'm assuming we have a nice DC coupled source. Again, maybe, you know, like I said, maybe a bass guitar or something like that, or, you know, a vintage keyboard kind of thing, okay, electronic keyboard. So you got a low, in that case, a low impedance out here. What would I have looking back through the inverting input? Well, I want to get that same resistance, 1K and 1K. By doing that, we can minimize the DC offset. We're not going to get rid of it, but we can certainly minimize it. All right. Now, granted, if your source here has a really high internal resistance, this isn't going to match correctly. All right, and you will get some DC offset. You can modify this resistance. If you know you're going to use a particular instrument and you know what that internal resistance is, you can go from there, all right? CF1 is here to short out RF1 at audio frequencies, because this resistor is going to produce a noise voltage. The bigger the resistance is, the bigger the noise voltage. So what we do is we shunt this with a capacitor, and that capacitor basically makes this a short at audio frequencies, and that noise characteristic sort of goes away, right? We shunt out the noise. That's the way of thinking about it. If you do have some high frequency noise, like interference, like radio interference, you can add this little CN, this little 47 picofarad cap, okay? That actually produces a fairly high critical frequency. And it's set the way it is so that the input impedance stays high. The critical frequency on this is about 3.4 megahertz when it reacts with this Rn of 1K. But you'd say, well, why 3.4 megahertz? Why not, 50 kilohertz or something like that? Because if you do that, you're going to see your input impedance suffer, because Cn is what's going to essentially set the input impedance. That's shunting this. Right? We know this op amp, non-inverting op amp, has a huge input impedance. So if you calculate using this 47 picofarad, what the reactance is at 20 kilohertz, it's about 170 k ohms. So that's still a pretty big value, right? That should not be much of an issue, all right, as far as loading something, loading your instrument back here. All right, so that's pretty good. We see a similar kind of thing out here, okay? We have, again, the balancing with RP2 at 10K and the Rin value at 10K. So they're there to balance. And again, CP2 is here to shunt out this thing to minimize noise. We also have this extra CF2 across RF2, again, to limit high frequency potential interference. Right? So this critical frequency here is about 72 kilohertz, right? You do 1 over 2 pi RC on these two components, you get about 72 kilohertz. That will give you a loss at 20 kilohertz of only about, well, a little less than half a dB, right? So you're not going to hear that, right? So that's a nice little sort of tweak to the response. Now, when it comes to building this thing, all the resistors should be metal film resistors. They have the lowest noise. They're nice, stable, good quality things. The capacitors, ideally, you would like all of them to be polypropylene capacitors. Those are very high quality caps, low dielectric absorption. They have good temperature stability, accuracy, and so forth. Unfortunately, they can be kind of expensive and they can physically be kind of big. So the larger the capacitance value, the greater the problem. And I'm going to point specifically to CF1 over here, a 10 microfarad. That could probably set you back, that one capacitor, $5, maybe $10 for the one cap. It's going to cost more than the op amps, okay? As a fallback, and physically it's going to be pretty big. It's probably going to be a couple centimeters long. So as a fallback, what you could do there to save some space, to save some board space, to save some money, you could put a Mylar film cap in here, and that would still have a very nice performance. Not quite as nice as polypropylene, but still, you know, pretty good. All right. I would shy away from aluminum electrolytics. Those are notoriously not so good for audio purposes. All right. So the only thing I've left off here is the attenuator. Right. So like I said, if you want to tap off the loudspeaker, you know, the loudspeaker terminals, and some amplifiers have an output for that. You don't have to actually get inside, you know, for like an expansion cabinet or something. We need to bring that signal down. That's very easily done. All we have to do is insert an attenuator right here. The attenuator is really nothing more than an L pad, right? A voltage divider, like this. So the instrument comes into here, and I've got this set up for 40 dB, which would be, you know, a output from a power amplifier, for example. So you got 100K and a 1K. So that's going to give you 1/100th the signal. It's going to drop it down by 40 decibels. Right? If you don't need quite that much, maybe you're just using a little practice amp, or you just have an instrument that's got a really hot output and you just want to bring it down a little bit, well, you could knock that down to a 20 dB pad, just change R2 to 10K. You would like to hook this in with a DP-DT switch. This is one way of doing it. So you would have a switch out here. Right, so you imagine you've got this input 1/4 inch jack, which would be typical, right? And you could go to the normal input that was on the preceding circuit, or you could go to this input, right? So you switch up, you switch down, and then you do the same thing on this side. You switch this one up and down. Why do you switch both sides? Because if you just left this directly connected, then this 1K winds up shunting your input, and that sets the input impedance for the whole circuit, which is not what you want when you don't have the pad. So you want to get that out of there, right? Another option is to just have a second physical input. In other words, have another 1/4 inch input over here and another, you know, the normal 1/4 inch input, right? And then you could bring those in and just have a single a DP, let me get that right, an SPDT switch to go between those two things. Or again, you could get a switch that has, a connector that has a switch built into it, and you could use that. All right, there's a lot of ways you can configure this. All right, so that's what you'd be looking at for the attenuator. So what do we get for performance out of here? Well, let's do a transient analysis. Bring this over here. And get a legend. Okay, so here's our generator, which is actually going to be laid over on top of the in-phase output. You can't really see it, but it's, if you notice, this color isn't quite right. It should be this maroon, but it's these two colors. One's behind the other. So every now and then a pixel shows up one of the other colors. But the important thing is the antiphase, right? The green is in fact perfectly an antiphase, and it is the right amplitude. The same exact amplitude is just flipped, right? Antiphase, 180 degrees out. Beautiful. All right. What about the frequency response? That's a good question. So we'll do an AC analysis, AC transfer characteristic. Let's see what we got. I'm going to open this up a little bit. And again, get a legend over here. So we can see certainly at this range, right? Here's 10 kilohertz. So below 10 kilohertz, these things are identical. The gain is 0 dB. So unity, everything's looking good. We are seeing a little bit of a difference at the high frequencies. So the green, the antiphase output is rolling off earlier, and that's because of this CF2 reacting with RF2. That's the thing I said that is critical about 72 kilohertz, which we can verify. All right. Your calculator says 72, and the simulator says 71. Yeah, it says 72, right? It's minus 3.03 dB, and it's 71.968. So it's 72 kilohertz, okay? So when you come back to 20 kilohertz, the upper limit of human hearing, we can see that's less than half a dB. It's, you know, about a third of a dB down. So that's looking pretty good. All right. And then we can see that the straight through, the in phase, that's flat, you know, beyond 1 megahertz. Okay. So like I said, if you are having some interference issues, you could always throw this in, and you could have a switch on this, right? You could put this in, just have a little contact switch, SPST contact switch, to bring it in or out of the circuit and be done with it. Okay. All right. So you can see this is a little different than the circuit that we looked at for just a simple phase splitter, which is more of like what I would have, let's say, if I was designing maybe a modern keyboard and I want to have, you know, a balanced XLR output. All right, I could just literally use what we used in that other one. But there are things that we need to add here because, right, well, it's battery powered. I don't want to put the batteries in backwards accidentally. You know, I might be, like I said, using a large input accidentally. Oh, I forgot to turn on my attenuator, you know, the attenuator switch. So I got a little protection circuit over here. Right, so these little things come in just to kind of tweak it all right, for that kind of application. And of course, you know, my final comment here is you can just get a dual op amp. Instead of using, you know, like an LF351 for these, you can use an LF353. Okay, that's a dual. A nice 8-pin mini dip package. You know, one of the issues with some of the more modern op amps is they're really only readily available in surface mount packages. You know, and if you're a hobbyist and you want to build one of these things, that can be an issue. And maybe you don't have surface mount soldering gear. Okay, so yeah, it's nice. You can still get some of these op amps that were designed, you know, 30 or 40 years ago. They're still available in these 8-pin mini dip packages. Hey, that's standard, you know, through hole kind of construction. You can build this thing up on a little proto board, solder it up. Everybody's happy. All right. Okay, so you got a lot of options here, but this is a nice place to sort of start. Okay, and you can tweak it as you need it. And if you have any questions, by now you should know to leave them in the comment section, and I'll address them at a later point. All right. Okay, have a good one.